Okay, good afternoon, everybody. So I realize this is a tough time to come and sit in a lecture, right? Post lunch, but hopefully it'll be okay. So we'll continue with the things, basic aspects where we said a little bit yesterday about the standard model and what the problem of baryogenesis is. And we, just to recap, the main point was this Sakharov condition. So that there are three Sakharov conditions which we would like to incorporate into any theory which can explain the baryon asymmetry of the universe. So the three Sakharov conditions, just to repeat, was what was the first one? Baryon number violation. And then C and CP violation. And then third one was out of equilibrium, departure from thermal equilibrium. So these get encoded as a Sakharov condition, so we keep track of these three. So whenever we try to look at any particular proposal for what might explain the BAU, remember, is the baryon asymmetry of the universe. We would like to ask, does it have each of these three ingredients? And if it lacks any one of them, then there's no point in looking at that proposal, because the claim is that it would not generate the BAU. So we looked at, it's kind of obvious that if we start with the universe being with zero baryon number in the beginning, then if baryon number is not violated, then it will continue always to have zero baryon number, and that's not good. So that needs to be violated. So C and CP violation, here also we saw, I might not have actually said what C, I may have said C is some particle going into this. What do I mean by this C? This is just on a field, it is a conjugate, right? So if this, let's say, creates antiparticles, this will create particles, and vice versa, right? So it has the conjugation. And so under a C transformation, you go from something which is particle or antiparticle like to its conjugate, the antiparticle or particle, right? So C violation means that, as we said, if there is some process happening for particles, the C transformed version of them may have a different rate, for instance, and that will be what is called a C violation. So we would like that, and this is, C is nothing but particle antiparticle. Interchange, right, under C. Now P is the coordinates, right? We flip the coordinates. It's like looking at it in a mirror, right? I mean, that's the P. I didn't explicitly say it, I realized, but what I was saying is a consequence of that. So it interchanges left and right fermions. You can convince yourself that if x goes to minus x, then this is what happens to a particle with spin. And so I was pointing out this one, but this is actually the definition of what we mean by the parity transformation. It's x goes to minus x. And I didn't say it yesterday, but there is also time reversal invariance, where here t is kept unchanged, right? Here we'll take t to minus t, and we'll keep space unchanged. So one can think about this transformation also. Last time I didn't include it in my analysis. Today we'll have a need for this t invariance, which I'll talk about. But generally these are the three discrete symmetries that people look at, and they are very useful in analyzing theories and what they do and what consequences they may have and so on. Rather than doing lengthy calculations, if you just appreciate that there is this symmetry or there is not this symmetry, especially when there is a symmetry, they'll have consequences which are easy to state, and without doing any lengthy calculations you can get at the result if you keep track of these symmetries. So therefore they are quite useful as we are doing here. We didn't do any calculation, but we said, okay, if there has to be a departure in the baryon number, you must have C violation. Without doing any calculation you can make such statements, and therefore these are useful to keep track of. So that is something that I wanted to just add to what I said last time, and also have a recap of it. So we will see more about it as we go along. Today we will focus on this one, departure from thermal equilibrium, third condition. Yes?
The CP violation can be also stated other ways, time reversal invariance violation.
True. Okay. Okay, maybe we can say that right now. So there is a result which says that every or a local quantum field theory must be CPT invariant. So there is that statement. So if you take that statement that CPT is a good symmetry, right? If that is true, then if you have CP violation, it also implies time reversal violation, right? If CPT is to be good, then if CP is violated, then T must be violated, right? And so this is an aspect which you can use in your, like analysis. If you have CP invariance, you could have equally well said that this is T invariance violation. Yeah, that was your comment, I guess. Yeah, so that is a true statement. And we are going to look at in this lecture, or what people usually do in phenomenology, in particle physics, is always a local quantum field theory. Or I can write it here. Right. Sorry, you wanted to make?
No, I just wanted to ask you, so that is also very important, that the C asymmetry means that the baryons and the antibaryon reactions are not equal.
Correct.
The rates.
That's right. Yeah. So this is easy to state because we want an asymmetry between particle and antiparticle. So it's kind of obvious to us that it should have C invariance violation. But CP is a bit subtle because, as I said in that example, you could have C violation, but so you can have this one not equal to, let's say, rate for psi L not equal to rate for psi conjugate L, right? We could have this thing, and we could have psi R not equal to, this means C violation, right? But it could happen that the rate for psi L is equal to, and the other one. This could happen. This is C violating, right? But it is CP conserving, right? And so if CP is conserved, this can be true, but C could be violated. And so what we think of as the asymmetry is actually the asymmetry. The total psi is left plus right, and the total psi C is psi C left plus psi C R, right? So if this happens, the total rate for psi and psi C will be equal now. Even though C is violated, we don't have an asymmetry in the end when I look at the total count of particles versus antiparticles. So this is why it is stated separately. If you have just one of them, it is not sufficient. It's quite easy to see that we must have this, but this is a bit subtle, but even that is not too terribly subtle, but it's like. And therefore, Sakharov already in the beginning stated it as two conditions. And as you say, like T violation is implied by assuming CPT invariance. because that also forward reaction and backward reaction should not be the same, right? And that we say as, we think about it as this one, right? But there are implications to T invariance there as well, right? What goes forward and what goes back and so on.
It already say that the chemical equilibration will be different because the forward reaction and the backward reactions are not same.
That we need, right? We need the forward reaction and the backward reaction to not be the same.
Yeah, but
Yes.
that also is included in the third statement, or there is something more
Which
in
is
the
the third statement? Yeah, that's right. Yeah. So maybe this is, I'm not entirely sure whether, if you say that it is a local quantum field theory, then maybe you can drop one of them, I'm not sure. But maybe that's something to think about, yeah? But it may be more general that this is independent of that statement, these conditions might be what you would state. And then it's not so obvious that CP invariance means T, or CP violation means T violation. That's not true, right? It's only true in a local QFT. So yeah, that's something to think about. I'm not quite sure how to say that. Okay, any other questions about last time? This is all what happened last time. Okay, so the thing is, we will focus on this one today, and our way of implementing this in many models or proposals that have been put forth is to put this particle physics setup in an expanding universe and say then that when the universe expands, the processes could go out of equilibrium, and the third condition also will get satisfied, and maybe it will leave a BAU, right? So we would like to understand a little bit more basic aspects of how to put this thing in the early universe, and that will satisfy. We have talked about this one a bit, and then we will also get some basic notions of the third one, and then we'll be able to look at concrete models and proposals and what they do and what are a few different kinds and so on, which will be what I will talk about in the remaining 2 lectures. So today we will still deal with very general and basic aspects of what must be true usually in any given proposal, right? So we'll just keep it fairly general today also. And from next time we'll look at a few examples of how to implement these conditions in specific models and what they imply and so on. So that will be the plan. So we would like to do this in the expanding universe. It might not be obvious why expanding universe will mean departure from thermal equilibrium, but hopefully as the lecture keeps going on, it will become perhaps clear. So this one expanding, and we would like to say that it is at some temperature. There is a gas in this expanding universe at some temperature, and the particle physics, the microscopic degrees of freedom, are the constituents of this gas. And so that CP violation and all that is present in the microscopic constituents of this gas, and the processes are going on, and we will make some thermodynamic statements about this gas. And our starting point would be close to equilibrium, because otherwise it will become very difficult to handle. So most people start with close to equilibrium, and since it can work by being close to equilibrium, then why not just do that and leave the hard part to somebody else, right? We'll just do the easy part. And so this is what we will talk about today. How do you put this, how do you make an analysis of this particle physics in the expanding universe? So for that, first let's look at how to model this expanding universe, and then we will add the hot part, and then we will get our basic formalism all done. So what is the expanding part? So that is encoded in what is called as this Friedman, Lemaitre, Robertson, Walker. And this metric is the metric of the universe, and so that looks like, okay, how many people have had some or is knowledgeable about some basic things about general relativity? Okay, good, that's almost everybody. So the metric will characterize space-time. So let's just write down what kind of a metric that we are going to consider. This is, by the way, standard cosmology. If you go outside of this, you're doing non-standard cosmology. And we will certainly stick to standard cosmology. This is usually called as d omega, the solid angle, or squared. Okay, this is the time part, this is the spatial part, and so this k here is the curvature. Okay, from your general relativity knowledge, hopefully this is clear what this means. And if I say that this is a metric, there are some, now there is one function here, which is, what is this, a of t. And so there is a scaling of the spatial, this is the 3 space part, right? The entire 3 space part is being scaled by this a of t. So this is called as a scale factor. Right? And it is a very simple thing. It's just as a of t, if a of t increases, lengths increase, right? It just scales all of the lengths by the factor a of t. And this form, one more thing I should say is that we will set k equal to 0. Because in the beginning, it was not clear what kind of a universe we live in. We could have lived in a positively curved universe or a negatively curved universe. K greater than 0 means positively curved. K less than 0 means negatively curved, and k equal to 0 means flat universe, right? So it was not clear earlier, but today it is clear to us that we live in a very flat universe. There are some tiny error bars on this thing, but better than, a sub% level, k is 0. So we will just think of k being exactly 0, and then that our large scale structure is flat. So we'll just set k equal to 0, and so that will get rid of this thing, and then you should recognize that this part with k equal to 0 is just flat space but written in spherical coordinates, right? R theta phi, right? So this is just a coordinate, like description of flat space for k equal to 0. And this is the time part, is a very simple metric, and this one is called as an isotropic and homogeneous universe. There is no special direction, there is no special place in the universe. Everything is pretty simple, and so this is the simplest expanding universe you can think of. And so now what does expanding mean? Expanding just means that a of t changes, a changes with time, right? That's why you say a of t. And so as time increases, if a increases, then you expand. You expand the space, 3 space part. And so that's it. I'm being a bit slow here because not everybody raised their hands last time, or majority didn't raise their hands last time when I asked about, are you familiar with cosmology? But if this is all something very familiar, it's okay, just bear with me for a few minutes, and then we'll get to some hopefully non-trivial things. Okay, so for k equal to 0, then I can get rid of this, and let's get rid of this. And so what is this a of t then is going to tell me this t is the cosmic time. So in general relativity, there is this coordinate invariance, right? You can reparameterize all of these in any way you like, but we will stick to this one, and whatever has the frame in which the metric has this form is what we will adopt as our frame, right, in cosmology. And so this will be the cosmic time that we'll keep track of. You can reparameterize these, but I'll just stick to this one. So A of t now will, if we want an expanding universe, as t increases, A of t better increase, right? Otherwise you will be in a contracting universe. So let's say we have this behavior where I would like it to go like square root of t, I believe. So something like that. So let's say A is, what is it? Goes like, yeah, square root of t, is it? Yeah. So that's in the radiation domination. And then in matter domination, it will go like t to the 2/3. So these hopefully will become clear later on what these things mean. So if we fill this space-time with some matter, Einstein's equations will relate space-time curvature to matter, energy density, right, and pressure. And so if you have only radiation, then the scale factor, if you solve Einstein's equations, I'll write it down in a minute. So it will just give you a solution which goes like square root of t. So this will increase with time, and so we'll be in an expanding universe. And if you fill it with non-relativistic matter, then it will, the scale factor will go like t to the 2/3, right? And so that will also be an expanding universe, and so it will behave like that. So this is something to keep in mind, that this can be solved for, and the equations that relate them, I'll just write down in a moment. And of course, as you know, that the observation evidence for an expanding universe came from Hubble a while back, more than 100 years back. And so that he said that the velocity of recession of a galaxy is proportional to the distance, right? So the farther that galaxy is from us, the higher the velocity of recession is. And this constant of proportionality is what we were already writing last time. This is what we call as the Hubble constant, right? I don't know where it came up, why did it come up last time, I forgot, but we already said something about H naught and all that, right? So what about this thing? So how do you make all of this come out? And then we have given the metric. So now we assume also the form of some stretch energy tensor, which means matter. So that is, I won't write down the full Einstein's equation, solve for it and give you all the equations and everything. That's part of anything, you can open any standard book on cosmology and you will find all of that. So I'll just write down the final result. You can solve Einstein's equation in this kind of a metric, and then the answer will be with some, you will assume some energy, stress energy tensor which has an energy density in P, right? And so if you write down Einstein's equation and solve them, you will get what are called as this Friedmann equation. And the Friedmann equations I'll just write down. Oh, one thing before I write that down, I wanted to say in this context, so since this A of t appears as an outside scaling factor, what I could do is to have a grid of space-time where I can say that, let's say I call this as some vector x hat, and so I can say that there is a fixed foliation of space-time, right? And so this will be some coordinate system that I set up And then if I say that this thing gets multiplied by a of t and all length scales are now, if a of t is bigger than 1, then all length scales are stretched. It becomes, bigger grid. And so here I would say that this is the coordinate x, which now is a function of time because I scale these with the scale factor, right? So that's the picture to have in mind, that there is some foliation of space-time, and this one is a fixed grid, but given that the scale factor itself is changing in time, that all distances are scaled. And so this one is what is called as co-moving coordinates. And this one we can call it as a physical coordinate. Right? So this is very common terminology. If you take any paper to do with cosmology, they will always be either, sometimes they will refer to co-moving coordinates and sometimes to physical coordinates, but all they mean is this one, that if you take a fixed coordinate system, that you call it as co-moving coordinates. Now you can analyze this gas that we have in these coordinates also, right? It's a perfectly fine coordinate system. Anytime you want to translate it to the real universe, all you do is multiply all of that by the scaling factor a of t. You should know how things scale, and then you can always multiply it. So you can take the gas in this coordinate system and look at all the processes that go on. Is the baryon asymmetry generated in this coordinate system or not, right? It's a fixed box now, right? Or you can do it in a physical way where you analyze things in this physical thing. Here you see that if you put like 10 particles in this volume, right, and a of t changes, if you say that I'm now going to count in this physical volume, it will be lesser, right? So number densities will just decrease in physical volumes just because the space-time is expanding, right? And so that's something that is a consequence of this picture, that there is an expanding universe, that if you have some fixed number of particles and they are in this expanding universe, if you take a particular region of space, then the number density goes down just because space itself is expanding, right? So that's an immediate consequence that we will have in physical coordinates. But if you analyze it in co-moving coordinates, the number will stay fixed, right? So that's, you can do it in either way because we know the relationship between these two. So that was just an aside because it's a very common thing for people to do it either in this or that. And this is also probably immediately obvious to you that if I now have a gas, right, and then if I look at quantum, modes in this volume, there could be some mode which is like that, right? And so in physical coordinates, it will be like that, right, equivalently, right? And as the universe expands, this mode, the wavelength increases, right? And so therefore all modes will do that. And if the wavelengths increase, the frequency decreases, and frequency is a measure of energy, and so all energies will drop. So if you started with some temperature and wait for some time, right, all energies will drop, which means the temperature drops, right? So it is a very simple picture that as the universe expands, the universe cools, the temperature drops. And so that's an immediate consequence, and you can convince yourself that the temperature just goes like 1 over the scale factor. And you can show it, all of these, much more rigorously, but I'm just giving you some hand-waving arguments if you have never seen these things before. So as A increases, in other words, the scale factor increases as time goes on, all temperatures will drop, right? Yeah.
At some point we will have two, let's say two planet or anything celestials, so we will measure their force of attraction using just Newton's law.
Yeah.
And then after let's say some years, we will again measure the this force. So by the difference in the force, can we evaluate this A of t, at least some zeroth order expansion parameter it can give?
Except that you should do a back of the envelope calculation and ask yourself how long must you wait in order for that expansion to become observable to you, right?
Okay.
It will happen such an incredibly tiny amount for such small scales that you will have to wait probably for like a 10 to the 500 years or something before you can even see the effect of. I don't know, I'm just making up this number. It's some worthwhile exercise. What question you asked, just like try to estimate how long must you wait given the fractional changes, let's say 10 to the minus 6 or something, right? A fractional change of 10 to the minus 6, how many years must you wait? A worthwhile exercise to do, right? It's just that it will be very long time before you can. So the longer you look at, the longer scale you look at, the shorter time you have to wait in order to see the effects of this expansion. Therefore, these effects will start becoming important only for cosmological distances. We are talking about the scales of like tens or hundreds of times the scales of galaxies, right? That's when you start seeing the effect of this Hubble expansion. But otherwise, very locally, you will not really, I mean, it will be a very tiny effect. But it will be there, I believe, so yeah. Yeah.
This 1 over A, is it same for radiation and matter? The temperature falls with 1 over A?
So just hang on 1 second. I'll write down the relations. It will become clear to you. Right? That's a good question. Yeah, it's not the same, but yeah. Any other questions? Like, move on. Yeah. So let me write down the Friedmann equation that I started writing. So this Friedmann equation is not T goes like 1 by A. So this one is, we will now assume that there is some radiation. I'll call it as gamma or R. Luckily, gamma and R are the same symbol. So radiation or photon, photon is radiation. So this is, let's say, radiation. Yeah. So they will also be radiation. So yeah. So this can be now rho gamma or rho nu. That will be rho R now. I'm supposed to say this as R now. Yeah? Okay. And then this is matter. And you can contemplate one more simple thing. Anybody knows what that is? What is the, Well, postdocs are not allowed to say anything. Okay, anyway, he said it. So there is vacuum energy. So that is something that we can look at, which is a constant energy filling space-time that never redshifts, right? So that is something that we can look at. So this is vacuum energy. Is this visible? Okay. And this is also called as a cosmological constant. And so if we have these three filling the space-time, and then we solve Einstein's equations, you will get these equations. You will get two equations which are called as the two Friedmann equations. Oh, so somehow I put back K here. That's okay, we'll set it to 0. So this pressure is relevant only for radiation. So for non-relativistic matter, we'll take it as 0 pressure. And so if you have this matter on the right hand side and you put that background metric on the left hand side, the only unknown that you have there is A. And so this equation tells you how A behaves as a function of time. So now A dot means dA dt, obviously. So these are derivative with respect to cosmic time. So this tells you the acceleration of the universe. This tells you something about the expansion of the universe, right? So these are pretty standard things that you'll find in any cosmology book. So now we pretty much have all of the ingredients. The rest of it is all analysis, right? We will assume some kind of radiation filling this cosmos and some kind of matter, and maybe you have vacuum energy, who knows. Put all of this together and we have some particle physics model that is making up all of those, right? And so you have to analyze all of this. That's where we are going towards. So we want to set up all of the basic formulation. And so given any particular particle physics model, we want to then solve that system, right? And so that's the thing. So for radiation, if you look at how these things, if you solve them, we'll just write the character of the thing. This is, I believe, what the question was about. So this radiation will go like the energy density in radiation will go like 1 over a to the 4th. Energy density in matter will go like 1 over a cube. This means non-relativistic, right? And the energy density of the cosmological constant is constant, which is why it's called the cosmological constant, right? And so this is something that you can just show using those things. And one definition that is usually made is this h of t is 1 over a dA dt, which is also written as a dot by a. So this one is the analog of the Hubble constant, right? So this one, h changes with time. It's a function of time because a is a function of time, right? But this one evaluated today is what is this Hubble constant, which I just erased. So if you do local measurements, like very close in our galaxy neighborhood and so on, then what you will be looking at is this parameter today, right? Evaluated at T naught, which is today, right? And that value you just call as the Hubble constant. When Hubble was measuring the expansion, like how galaxies are receding from us in our neighborhood, very local, he was actually looking at h naught, which is why it's called the Hubble constant. But in any epoch, h is not a constant now, it changes with time, right? It just is given the same symbol h of t. And this g here is Newton's constant, right? So it is also, you can derive a Planck mass from it, which has that relationship. What we usually think of as Planck mass is just Newton's constant 1 over gn, 1 over square root of gn. Yeah, sorry, you had a question. What is the k? So which I said equal to 0, that is a curvature. So if k is bigger than 0, then it's positively curved. K is less than 1, it's negatively curved. K is 0, is flat universe. Capital lambda is a cosmological constant. That's that thing there, right? It's just a constant energy density in space. And it has the value lambda. It's a number.
So how do we get these equations, Friedmann equations?
Einstein equation. So you just take this, oh I erased it, you take the FRW metric or FLRW metric, you assume that there is radiation, right, or there is matter, or there is lambda, right, or you put all of them, right, solve Einstein's equations, then you will get that.
So
Given the metric, you can solve for all of the components of the,
so when you're going to
the
put this,
curvature terms, right?
when you're going to put this rows,
Yeah,
so you will be putting together the radiation part and the matter part.
yeah, addition. If you have some radiation and some non-relativistic matter, if you have both of them, just add the energy density. The stress energy tensor just adds all of them.
And how do you know that those functionality are exactly like that?
How that you can show by Friedman equation. You can show these things. We can maybe try to do that exercise later on. You can show that. Any other questions? Yeah.
So you are taking k equals to 0 in this
Yeah.
equation. So
Simply because that matches our observed. Universe.
it is now, right? So we are assuming at early universe also that k equals 0.
Yeah, k doesn't change with time. This parameterization is if you are in some curvature, it stays in that curvature. Yeah. Okay. Well, actually, we could be in a positively curved universe. Let's say you put k equal to 0.00001. Technically, you are in a positively curved universe. But because you are so small curvature, you will not be able to detect that in any experiment. And so maybe this one, if you do incredibly long scale experiments, you will become sensitive to this curvature, right? So we could be living in like a very tiny curvature universe. But observation, it has error bars, you can look it up, I don't have the number. So the k has some value 0 plus or minus something, which is like 10 to the minus 3 level or something. So the curvature is flat to a pretty good accuracy, but we could be either in negatively curved or positively curved, we don't know, yeah.
So what are the experiment is telling us that it's very tiny positively curved?
I don't know how to answer that very crisply, but one of the things is CMB. So the multipole where the first peak appears, if you look at the oscillations of the plasma, the CMB oscillations, the plasma is oscillating, right? And so there is power at various scales. If you look at the first maximum, you can work out what is the actual scale of that. Given QED is known, right? This physics is known, the microscopic physics is known, and you can work out the oscillations, and you can say how the power is distributed, and the position of the first maximum will tell you what is the curvature of our universe. So that is one place, but it is actually a concordance. Everything in cosmology is concordance cosmology, right? You take this particular FLRW metric and you put all of the observations into it, and then you fix all of the parameters, right? And there will be best fits for all of that. But the position of the first peak most crisply tells us that the universe is flat. That's how I remember, but we can check this thing.
Sri, I have a question.
Yeah.
So, what do you mean by a positively curved and a negatively curved universe?
So it is like living on the surface of a sphere.
Ah.
Like if you take the two-dimensional analogy.
Yeah.
So if you were to be a two-dimensional creature living on a sphere,
Yeah.
you would encode that with Ka positive. If you live on a saddle, that's supposed to be a negatively curved space.
I see.
And if you live on a tabletop, like here, you would be K equal to 0. So now that you just transpose to
What
three
would
dimensions.
be the implication of a negatively curved universe in terms of observation also? I don't know.
Now that angles, how angles, like an intrinsic angle. If you take some angle in the sky, here you have some angle. If you're in flat, right, there is an angle and you have an observation here, right? This is my eye, right? So if it is flat universe, the apparent angle and intrinsic angle are the same. But if you have negatively curved, I believe it will do that, right? I'm not like that, but if you have a certain angle, the measured angle will be more, right? So it's just like living on a sphere. If you live on, and the other way is like, if you live on a sphere, it will be like this. If you have some angle, it will appear smaller. So there will be that kind of consequences of that. But anyway, we don't need any of these things for our purposes, but yeah.
So one very naive question.
Yeah.
So could you tell about little bit of this vacuum energy?
I don't know what more can I say. So these things redshift, right? Meaning that as A increases, their energy density all goes down, right? Because you can think of it as the finite energy of the universe or something. The cosmological constant is a very different beast. It's a peculiar object. It's like it never goes down. So per unit volume, energy per unit volume always stays the constant, right? Very bizarre, right? The universe is expanding, so it's just like the total energy of the universe keeps increasing, right? It's just like, it's a very simple thing to do in the equation. You just add a constant term, right? But it has all of these aspects to it. And of course, if you put that thing crazily, what we have measured now is a non-zero value for lambda, right? That brings all of these complications. Otherwise, you could have conveniently forgotten about it. But lambda comes out to be a non-zero value, and so now you are having to confront this thing. But it's a very crazy object. Yeah.
What could be the origin? Like
Nobody knows, and it's like one of the big unsolved puzzles in all of science, if you ask me, right? But yeah, what is the nature of this lambda? And it's like nobody has any good ideas. Many people have tried. There are some maybe half ideas, but who knows? Yeah.
Thank you.
So all of this we don't need. So this is all a big aside. So what we will need are these kinds of relationships. And so the question that was asked, so here when we say temperature, we only think of basically keeping track of relativistic matter. So radiation to us is what counts for everything. And if you look at radiation and say that it is characterized by a certain temperature, right? Then if non-relativistic matter has coupling to it, fine, but we'll just keep track of temperature, the heat path, as being the relativistic degrees of freedom. So that will be the dominant one anyway. And this particularly makes sense because for late time, let me know, that's actually going the other way, so let me not say anything. Yeah, okay, that's the thing. Temperature is characterized by the relativistic matter. So I forgot, you asked this question, right? I forgot. Somebody asked. You asked, sorry, yeah. So for radiation, this is true that I am saying that there is some wavelength. For non-relativistic matter, I will not think about it like that. No, it's like it is just some wavelength is there in physical space, and then it remains fixed independent of whether universe is expanding or not, right? But for relativistic thing, I'll think of it as a particle in a box. The box itself is expanding, and so that tells me that the temperature goes like 1/8, and that is the quantum picture that I have in my mind, right? That's one way to reconcile that. For non-relativistic matter, it just redshifts simply as the volume. So if rho is just the mass per unit volume, right? This is a physical volume now. So physical volume here in my notation means this x. Let's say I look at 3 space and volume will then be, this is physical volume, which is like this delta x. I take 3 of these and that will be my volume, like small volume. And now if that is the case, then in terms of co-moving things, it will look like this will be AQ delta x hat cube, right? So if I have some number, some mass density, and the physical volume itself is scaling like a cube, then the density will scale like 1 over a cube. Right? That's all this is saying. Yeah. For temperature, you do this, plus it is also red shifting, right? Radiation is red shifting because of the particle in a box kind of thing. It sees the entire volume. And so you get this extra factor of A, and it goes like 1 over a to the fourth. Which is why I have that picture in mind, that for radiation it really is seeing the full extent of the universe. But for matter you can think of it as just decoupled in some clump, right? I mean, it's just some clump. It's not sensitive to the thing. So this is pretty much in all of this is the thing that we'll need, whenever you analyze all of these things, this knowing how these different components redshift is something very useful. One consequence of this is that if you wait long enough, radiation drops out, right? Because it is going like 1 over 1 power of A in the denominator bigger, if you start with some energy density, this is the thing, and then matter will go like this one. Right? This falls faster, 1 over a to the fourth. Oh, sorry, what is this? Is time. Time or a, whatever. Yeah. So if you start with something and you wait long enough, radiation will become subdominant. You will be dominated by matter. Sorry, yeah. Correct. So all of the physics, if you take a small enough region, we must have standard physics.
Yeah.
Otherwise we are ruled out. No point in talking about cosmos and all that if in a tiny region you don't have standard physics. So every single law that you know, if you do local measurements, it will always hold true. But we are talking about incredibly large scales here, where things will get non-trivially modified. All local measurements, all of the physics is true. Special relativity is true, then all your thermodynamics is true, quantum mechanics is true, everything is true. Stefan Boltzmann law also is true. Yeah. And of course that lambda, this crazy beast, is always staying constant, right? It never redshifts. So this tells you that you wait long enough, everything redshifts away, right, to incredibly small values. All that you have left is this lambda, right? And I don't know if I have, so here you can actually conclude that you will actually have an inflating universe, if you solve those equations, that A will exponentially increase as a function of time if you only have lambda. So the fate of our universe is that if you wait long enough, that it will just get into an inflating phase and will just inflate away everywhere, right? It's like, so that is because we have actually detected a non-zero lambda. If you wait long enough, everything else will redshift, but only this one will always stay constant. This is an incredibly tiny number. If you don't know, this is 10 to the minus 3 eV to the fourth. This is the measured value, right? It's a very tiny value, but it is finite that we have measured. Right? And we are already in a phase where we are somewhere here today, where in fact vacuum energy is dominating, right? So that's just an aside. Yeah, yeah. You can have? Sorry? Like neutrinos, right? Neutrinos very light.
Yeah, so then you cannot really assume matter is non-relativistic altogether, right?
Correct. Neutrinos
Then you
is,
may
counts
have
as
connections
radiation.
to all these arguments that you made here, right?
Yeah, so neutrinos counts as radiation.
I see.
At present, you wait long enough and the universe gets, because right now the universe is at a temperature of 2.73 Kelvin, right? That's the average temperature, which is large scale average temperature of the universe. But neutrino masses are of the order of 0.01 eV, right? So now I have to convert this Kelvin to eV. So this is what? This is 10 to the minus 4 eV, right? Oh, actually the heavier ones are becoming non-relativistic. Sorry, yeah, that's right. So the average temperature right now is 10 to the minus 4 eV.
So at present,
At present, the neutrinos will count as non-relativistic matter.
I see.
The heavier ones.
I see.
Who knows what the lighter ones are, right? We still don't know. And they will count as radiation.
I see.
Whenever you have average, energy, much bigger than the mass, you think of it as radiation. And baryogenesis happened so early on that for then, neutrinos certainly relativistic and all of the standard model degrees of freedom relativistic, right? But now they're all non-relativistic. Protons, neutrons, all of them have become non-relativistic. Yeah. Yeah, thanks for that. Yeah. Okay, so I'm taking way longer than I had intended on this thing. Let me just quickly write down a few more things and go on to something else. So now we do the standard things in thermodynamics, given all of this. Let me just write down the standard relations, a few of them that we'll need, and then we'll move on. So we have this distribution functions. We can have the Bose-Einstein or the Fermi-Dirac distribution functions. This is a function of momentum, right? So this is, if I keep track of quantum distribution, so it will be like right. So for bosons it will be minus and for fermions it will be plus. And the Boltzmann limit is what we'll use. So when these F's are, when the occupation number is small, you can just make your life easier, and then we will use the Boltzmann distribution. So E here is a function of P, right? In fact, the magnitude of P. And so this will be, give me 1 second. There is some sign problem.
Yeah. Should be E minus mu by T.
Thank you. To me, because I'm so used to Boltzmann, it should always be minus E. But here it goes in the denominator. Yeah, okay. So we will only look at this limit, and we can write down the forms of this energy density here. That so there is T to the 4th. So rho r will be, for the quantum distribution, it will look like so this is for Bose-Einstein and this is for Fermi-Dirac. And we have rho matter. So I'll just write it for the number density. So rho non-relativistic matter is just m times the number density of matter. Yeah. So this is something that we'll need for baryon density and so on. It's just the number density. And so the number density is what I'll write for Nm theta of 3 pi squared g t cube 1 d by 4. So the number density goes like t cube, and this g is the number of degrees of freedom. So for a photon, for the two polarizations you have g equal to 2. And you can work out in the non-relativistic limit, you can work out for the Boltzmann distribution what those corresponding expressions are and so on. I will not write all of them. This was just for illustration that you will have something like that. And so all of these expressions are worked out and in full detail in Kolbe-Turner. So he gives you all of the limits and so on. If you need any of them, you can just look up Kolbe-Turner's book. So one other relation that you can write down is this Hubble constant in the radiation. So as I said, I erased this thing, but in the beginning, when you have radiation will dominate, right? This was our graph. So eventually matter will become important, and at early times it will be overwhelmingly radiation because that goes like 1 over a to the 4th, right? And so in the beginning you will think of the universe as being radiation dominated, and in the radiation dominated epoch you have h of t given by t squared over m Planck. So you see that in natural units it will be like you will have the right dimensions if you have t squared over m Planck. So h is a rate, it is a dot by a, so it will be something in natural units, it will have GeV units, right? And so t squared over m Planck also has GeV units. So in the radiation dominated epoch, you will have at early times, perhaps we will do baryogenesis in the radiation dominated epoch. So at those times, h of t will be given by t squared over m Planck, and that g star is some degrees of freedom, but weighted specially between bosons and fermions. You can just look at Kolbe-Turner for the full expression of that. I'll not write down, but it is just basically the number of degrees of freedom. And if you just count all of the degrees of freedom in the standard model, you will get something like 100 and something, right? You count all of the quarks, leptons and neutrinos and everything, right? You will get 106 degrees of freedom. So it is a huge number of degrees of freedom early on, but the universe has cooled so much now to 2.73 Kelvin, and now if you look at the relativistic degrees of freedom, it is very few. It is just basically photons and maybe a few neutrinos. That's about it. And everything else has become non-relativistic, right? And so we went from some degrees of freedom of 106 to something like a few, now 6 or 7 or something like that now. So those are the things that enter there, that in the G star, but weighted by temperature depending on what there is all kinds of things that have happened. So E plus E minus is annihilated into photons, so there is some reheating of the photon bath because of these annihilations. So that G star keeps track of all of that. Like the individual species might be at slightly different temperatures because some species might have decoupled at some time. And so to keep track of all of that, you define the G star. But it's basically like G, but it is redefined. Yeah. I think that's pretty much all that we would require for analyzing this. Oh, one other thing is instead of just the n, it's commonly useful or commonly done to keep track of the entropy. So one can write down expressions for the entropy density. So if you have a gas, it has some entropy. And I'll just write down that expression because in any baryogenesis paper you will find that quantity being used. So this S is the entropy, and the small s is just the entropy density. Again, the entropy per physical volume. So if you do that, this is S. And this G star S is also degrees of freedom, but yet another, like reweighting with temperature. And so that is how it looks like. Because it's a density, it has T cube, right? Like our number density, except that it has different prefactors. And the reason why I write this is because people define this Y. This is called the yield variable, which instead of talking about a number density, you divide by the entropy density, right? So then what is going on is like this has an A cube factor, right? 1 over A cube, right? And this also has 1 over A cube because T, remember, goes like 1 over A, right? So S small s has 1 over A cube, and N also has 1 over A cube. And so that scale factor cancels out in this thing. And that is the utility of looking at this variable. So this is more like a co-moving quantity then, because you have taken out the effect due to the expansion of the universe, right? It just counts what is happening in a co-moving volume. It's like a fixed grid kind of picture. And that's a very useful quantity to have. Otherwise also you can do it, no big deal. You know the dependence of how the scaling is, so you can, but it makes expressions more compact if you write it in this variable. And that now is written in terms of, by the way, the notation that I will use is this N, wherever there was this chemical potential, right, this one. You can take a corresponding N and take out this factor of mu by T and define this N0. This is with zero chemical potential. This is a common notation, right? So the number density at zero chemical potential, we'll just call it as N0, right? And this is explicitly taken out. And so here you can write this yield variable, taking this e to the mu over T out, and then correspondingly that, right? So Y of 0 is with zero chemical potential, so that will have just N0 over S, and this you can write down in expression. You will have the T cube that cancels out, and unfortunately I have the more general expression, but you can work this out. Given the expression, it will be some simpler form. This K2 is the Bessel's function, a modified Bessel function of the second kind. Sorry, I can expand it and write it, but I have the more general expression. This is a fully general expression for all temperatures. But people usually write either the relativistic or the non-relativistic limits, and so that is a bit easier to write. But otherwise, if you want the full general thing, you'll have to write it in terms of the modified Bessel function. So this is an important quantity. The reason why I summarized all of this is I wanted to tell you the expression for Y. because when we solve for the baryon asymmetry, we are going to equivalently solve for this y. So for baryons, I can do the same thing. I can take the number density of baryons, which is the number density of baryons minus antibaryons, right? And so that's that n big B, right? Now I can divide that by the entropy density and get the yield for baryons, and so that has a certain value. So I had written down the value for the n, so I just write that value, plug in that value, and if I just divide by the entropy density today, right? So given that S has some, where was it? S has something, I can plug in today's temperature, which is 2.73 Kelvin, right? Then I will know the entropy density today, because I know what is the degrees of freedom today, right? So I can plug in all of that, and then I just divide by that entropy density, and what I will find is this number. Given that NB of some 6 times 10 to the minus 10 that I had, right? So I can correspondingly get this YB. So this is the observed value of the yield variable for baryons. And so this is very common in the literature. You will find people actually using this one. So this is the number to shoot for. So you would like to cook up all of your theories and whatnot, put it in the expanding universe, use all of these expressions, right? In the end, find out how much of it is left over, and you have to get this number. So that is the rest of the lectures. We will go through some examples where we take this machinery and apply it to a particular particle physics model and ask, can we get to this one? And some theories give you that, and some theories not. And what we would like to have is some understanding of which kinds of theories give you the observed things and which not. Yeah. There is an error on that. Sorry, I didn't write it down. So it is the same kind of error. So what we have in because this is just a like theoretically defined thing, so I just take the error simply due to n. Yeah, very well known. Yeah. So this S is not any measured quantity or anything. It's just a theoretical number that I supply. So G star S is so that is G star, which was in the rho expression, I believe. So this just, now here what I've done is to say that there is a gas with some number of bosons and some number of fermions, and if you sum them, then you can write the rho r in terms of this G star, pi squared over 30, and then G star T to the fourth. Think of that gas at a common temperature T, but then the individual species might be at its own temperature. Scale it with that T which has been pulled out, and then weighted G's are what is this G star. And similarly G star S is another weighted thing. Everything remains same except that because that scale says T cube, I just have this here, and so that's the G star S. So the same expression here, but wherever. S, what's in there? There it has been written in terms of the G star S. The same kind of thing. Maybe stop, because I wanted to start next with the Boltzmann equation rather than start a completely new topic now. Maybe we'll just take it tomorrow. Yeah, because I'm out of time. Lot of time went away in many basic aspects about cosmology, but it is fascinating. But if you have never seen these things before, it's fascinating. But that's not stuff that we need for these lectures, but it's okay. Right? Yeah. Okay, I'll stop here and then take up tomorrow.